Yeah.
Michael, it's not yet here. Today was especially a wrong day to show you that because I was really thinking I should have more time. I don't think I'll be able to finish. But so I told you guys that from next Tuesday onwards, I'll start special relativity, and then we will have 2 weeks for that. So how much ever I do today is it's better that this is the last day of classes. So that's all there is. But there's a homework related to this, and the homework starts by saying there is a resource with a video, which is a lecture from last year. So that sort of fills in the gap. So what I'll do here is that I'll give the full picture and maybe jump steps.
If you write a summary like the some background multiplying. Write a summary.
Oh, it is. Yeah, it is less than that because I will be able to do good bit here. Like Lagrange multipliers was where nothing was done in the class at all. And like looking back, I think I've done this 2 times, and I feel that it is not the best thing to do. It's like increasing the load of the class itself. This I wouldn't relate it with that because I will be covering it here. I'll give a reasonable picture of a problem. Except the details, like I try to go through every step in the problem when I'm presenting in the class. It's not primarily because I want to go through it. That's the only way I know how to go through it. Otherwise, I have to memorize the whole thing. And I don't memorize it. I just go through the whole problem in the class. So today what I'll do is that I'll reach a stage and then look into my notes and then jump steps. Kind of, that's what I'm hoping we can do without too much feeling that, oh, this is really off, without showing it as a magic kind of. And the details will be there in the video if you really want to. So that's my hope. And I was thinking I should do it. I was thinking, okay, today we just go and begin, and then I get distracted with this. That was not fun. Okay, so let's see how far it goes. Did I answer your question? Right? Yeah. So give it homework 10. It's due Tuesday, but that's just a formal deadline. We have been flexible with the due dates. Final exam. Did you guys think about how you want the final exam? You get a chance to discuss among yourself. Midterm 3, format was reasonable. Have 1 or 2 questions for the whole semester. And about 86, let's say 70% of the thing take home. Does that help or no? Yes, no.
That's what yeah, I like that in the math methods.
You like that?
We
You
did
like
we
it?
did that in math methods.
Yeah, and you like it. Okay. Yeah. If that is the case, I sort of know what's the problem I will give and for the take home. I typically do like in relativity, what you do is suppose you have a ball and you drop it, right? It falls down straight. It is half AT square. We all know if you start from rest, it is y is equal to half AT square, right? That's our kinematic equations. And immediately you ask what happens to this equation in relativity. If Einstein's equation is correct, then there is a maximum limit on the velocity. So it cannot keep accelerating, right? So this half AT square changes. It's no more parabolic. It is hyperbolic actually. So, but that's can be done in a lecture. It's reasonably, once you have developed the formalism of special relativity, it's reasonably easy to do that. But typically what takes a little more effort is that now you extend this problem, the same thing horizontally, you give it a horizontal speed, and we know that it takes a parabolic trajectory now, not in time. Earlier the problem was in time, it is already square. Now it will be a parabolic trajectory. And you do the same thing again, what happens in relativity. How does this generalize? And it's a little more work, but a tedious little work, and maybe I can make that as a problem, which will be broken into many pieces, and then we take home exam. It will be like a homework, long homework, and something I can think of, but I haven't decided on. That's something, and it will be very useful to at least have the insight for that. So, okay. So here I wanted to this called precession of the perihelion. Precession. Okay, it's a spelling. I think precession, is that correct? Like Owen in spellings. Okay, so what we mean here is that we have shown that if you have a two-body problem, we said the solution is an ellipse. So where one of the body is at, no, this is not. Yeah, one of the two masses is at the foci, at the focus of this ellipse, and one of the foci of the ellipse, and that's the second mass. And it goes around, and you will notice that this comes back to itself. Right? Like it starts from one point and it comes back. And one asks, is that really necessary or not? And for a Kepler orbit, by Kepler orbit we mean two masses and Newton's gravity being the only force, then it always comes back. And then you say, what if you perturb this? That is Jupiter sitting there. There are so many planets there, even though they're negligible, they're really tiny, but they do affect it. And can that effect really make this switch? And the answer is yes. If you're not in a Keplerian orbit, it is actually possible that you could have. Let me try to draw this. You could have this. And so on. Right. So what is happening here is that if you perihelion means the maximum point of the radius. Right? If you draw the length from the focal point of the one of the foci of the ellipse, what is the farthest point? That's the perihelion, and that keeps shifting. The farthest point in the second time it comes in is somewhere here, and it is somewhere here. So we would like to know what is this angular shift here. We will call that delta phi of this delta phi. How much is that shift? We would first like to define that shift in itself, and that's what we mean by precession. Precession of the perihelion. Precession means anything that rotates. The classic example is that of a gyroscope, like a gyroscope-like system. It is spinning. Think of a magnet in the presence of a magnetic field. It will actually spin. It can spin around, and at the same time, it can precess around the magnet. So that's what happens in a magnetic field, and there's a top, right? I mean, in classical mechanics, you do a top where again it spins and then goes around in gravity. Hopefully, you've seen those simple charts. So we want to analyze that. So let's go back and do our standard Kepler problem. So our standard Kepler problem is the Lagrangian is equal to, so it is half m1 r1 r1 by dt square or 2 by dt square, and potential energy is minus, so it is minus and minus, so it's plus. It's G m1 m2 over r1 minus r2 and the magnitude of that. And this always gives you precession to be 0. We will show that this is always 0. But now we want to add something to this. Right? We are going to add a small quantity which is having a letter kappa in front of it and some interaction. Right? So let's say there is some new interaction in there. And this is a dimensionless parameter. And we will require that the ratio between these two, so kappa, is going to be some number which is very much less than 1. We will, and that will be the idea of a perturbation series. Actually, talking about perturbation in the 10-minute video, just to connect it with the class. So that was done as a perturbation series. You cannot do it exactly. So you say that, okay, can we get the leading contribution at least? So similarly here, the moment you put in a third body or any interaction that is different from the gravitational potential, it becomes very difficult to analyze it. You cannot do this exactly. So we want to do this approximately. So we will say that this is small. And what's the first effect you can think of? Like what's the leading order? What's the, if you don't keep it, that is an answer. What's the change you can get from the answer? That's what we will try to, and in that change, what is the leading change? So that's what is called as perturbation, and that's what we want to keep. And typically the idea is k equal to k less than 1 and Taylor expand and keep the leading order terms. That's the basic idea. So let's go back and remember that this basically became, and when we try to get rid of the coordinates, we had a conservation of energy statement, which was the following. So this was 1 over 2 mu r dot square. So it's time derivative square plus 1 by 2 mu r square times the angle, how the angle changes. Right? That was how the angle changes with time. This is the centripetal, this is the contribution to the centripetal force, or sometimes it's called the centrifugal force. And then we had minus G m1 m2 over r. Now we want to talk about plus kappa. And since this is having the same sign as this term, so this will be minus. Energy flips that direction, so it's minus of kappa of infrared. And I haven't specified this yet. I will specify that in the next step, what exactly is the kind of interaction we want to keep. In that itself, we will make an approximation that it is only the spherically symmetric contributions we will keep. This we converted this statement into, we had this expressions, U naught is equal to minus 1 by 2 G M1 M2 over R naught. R naught itself was equal to help here. So that was LZ square, not LZ, LZ square,
Yes, that's it.
LZ square over mu
GM1.
mu G M1. And it's possible. Okay, so that's what that was. And in terms of those two quantities, we could rewrite this whole equation as there was U naught times dr. So there was R naught dr over R square d phi. Should write this as square. This is square. And this was minus mu naught times R naught over R the whole square plus 2 U naught R naught over R. This is not a function, this is a constant times R naught over R. And now this is where I give the explicit expression for this kappa. I write this as kappa times, see what I want to write. So I want to write this as 2 times U naught F of R naught over R. It's some arbitrary function, any function, but it should be dependent on only on 1 over R. There's only a R dependence in here. There is no theta and phi dependence. That will be the same as saying this one will be, so since there is a 2R I'm multiplying. Right, so this will be U naught times F of R naught. That's the same. That is not 2, I guess. Yeah.
Why did we write the last term of that?
That's just a, so, okay, so in general, L interaction can be anything, right? So that could be R1, that could be R2, that could be all dependent, that could be an R3, there could be a Jupiter's position, we're talking about a perturbation. There could be a lot of dependence in there. What we want to do is that we want to talk about a special situation where this is depending only on the R case by the time we reach here at this stage. So it's a very special situation, or you can say that the interaction, the perturbation is in such a way that it's mostly in the radial direction. Like we want to talk about perturbations, which is mostly radial, not in the angular case, just for simplicity. And or what I'm motivating here is that even without an angular contribution, you can actually have the precision coming in. That's another way of motivating. Does that answer it? In general, what you would do is that have the full interaction and then expand it out. So that will be a contribution from angle, that will be a contribution from direction, that will be a contribution from radius, radial direction. So there will be lots of contributions. You pick, this is an artificial construction. you say that one of the term is more dominant, and that dominant term itself is smaller than all this. Like, first of all, this has to be small, but there are lots of pieces in there, possible pieces. You say that I'm interested in, at this point, just for simplicity in the analysis, let's keep R. Right? With that, we can use our formalism as we have and then still get some limit. In general, you should keep everything. If you want to test real life scenario, you should keep everything and have a very significant reason to proceed this way. Yeah, actually, this is really what is happening. An answer could be, again, going back in history, they had predicted when actually in real context here, when they really saw the perihelion of Mercury, they couldn't explain it. Like before relativity was postulated, they could see all this perihelion angle, perihelion of the Mercury moving. And then the question is, what is it causing? And they were so good at predicting these things. So they predicted that there must be a planet inside the Mercury's orbit. And the only place where it can be there and you don't see it is that it's very close to the sun. So now imagine there is a very tiny planet close to the sun, and that's what is causing this. If you're really close to the sun, it's reasonable to say that the radial dependence is not, if you assume that. Right. And that was called Vulcan. I think last time I mentioned this, I couldn't remember the name of the planet. I think it's this Vulcan, if I remember correct. So that was postulated, but it doesn't exist. Or as of today, we don't know whether it exists or not, based on our technology these days. One would think that it exists, but who knows? I mean, that could be really. Planet is so bright, sun is so bright that you cannot see things around it. That's something.
The term is expansion.
This is one of the, so if you introduce that interaction, that will have R1 minus R, so it will be R1 minus R3 now, right? So that's a new interaction there. And that's not necessarily this form. But let's say that in all that expansion, when I change these coordinates from R1 to R, somehow this is dominant. That must be a good reason for that. I'm not motivated. I don't even know how, like that will be a good amount of analysis that goes from here to there. I'm just saying that given in our formalism, if there is a reason for you to have such an interaction, what will be the consequence of that? Can we say something about that? That's okay. Okay. If that's the case, then we can rearrange and get something very similar to what we had earlier, divided by U naught and put it back, right? So this you want to keep it on one side. Let me see if I got all this. Oh, there's a minus sign here. You do some jumping steps. That's a minus sign there, I think. That's all. Plus 2R over R naught. Yeah. Okay. So divide by U naught, take this onto the left hand side, and I get R naught times dr times R squared. D5. And that's a square, but I'm going to take square root on the right side. So this I moved it to the left. I'm dividing by U naught. That's a E over U naught. So I'm going to write this as 1 minus E over U naught. So I added a 1. And I subtract that 1, which I put it together with 1 minus R naught over R the whole square. And that's a square root of that. If the kappa was 0, that's your contribution. This we saw last time also. And now we have a kappa there. So it is plus kappa times F R naught over R. There's a reason why you do this. There's significant simplicity based on our solution. Okay, that's why I'm doing it this way. And only this particular format works. Like this is a very particular case, and it's not my construction. This is from Landau and Lifshitz book, so it's not mine. But there are some changes I make in the final answer. Yeah. Okay. And actually, it is not a treatment. He gives it as a problem, so the answer is not available. But then Landau and Little's, if you've seen that, if you read Landau and Little's book, the whole solution is almost described. So the solution is in a first paragraph. They give you enough hints. So there's a lot of construction motivation in the problem stated itself. Okay, so that's your construction, and we know if kappa was equal to 0, that's your that the solution is the ellipse, right? And we also say that this is E squared. We define this to be E squared. We could say here, E squared is 1 minus E over U naught. Okay. So so I can write this as, let me write d phi on the left. So this will be equal to, so move it down. So this is R naught, R over R squared. And this is 1 over square root of E squared minus 1 minus R naught over R squared plus kappa times F. Oh, thank you. Okay. Any questions at this stage? To first remind ourselves of what it is, right? Okay, let's do kappa equal to 0. If kappa is equal to 0, or actually before that, I should define my delta phi, right? So precession of the perihelion will be defined as delta phi is equal to do this d phi. I had to define where I go and where I reach, right? I start from minimum. Remember, in my case, I have my I choose the marks to be on the other side, right? That is how I chose in the earlier part. So we can choose either way, but I prefer to choose it here. And then this becomes the minimum radius, and that becomes the maximum radius. And let's, in general, if it is perturbed, we don't know where that minimum and maximum is. Let's go from minimum to maximum. Our definition will be, I go from minimum to maximum, and the time, the angle it covers there, if it is perfectly symmetric, it will be the same that it will take to come back. It is 2 times that. So then I get the full. I should come back in here. But if it is not kappa equal to 0, if it is perturbed, this may not be the case. So subtract this whole thing. Our minimum with R, it will be 2 pi. Right? The expectation is that this will be 2 pi. Right? If I go the whole way, if kappa was equal to 0, that should be 2 pi. So I subtract 2 pi. So that will be my precision. If it is not 2 pi, that means it is precise. To begin with, I should say for kappa equal to 0, what happens? So let's calculate this. So this is kappa equal to 0. So moving on. So let me do 2 times our minimum to our maximum d phi. That's the same as you go from 2 times our minimum. This time kappa is equal to 0. So this is our minimum is, let me write our minimum itself at this point. That's our maximum times R naught dr over R squared. And that's 1 e squared minus 1 minus R naught over R squared. Oh. How do we proceed here? This is the important step. Notice this mathematical substitution is exploited. That is why we construct this problem here of this form. What you substitute is 1 minus R naught over R is actually E times cosine theta. If you notice, this is pretty much the solution. Like this is the solution as an ellipse, but that came out that theta was equal to 5, but otherwise this is pretty much the solution itself. And this is the same substitution we are going to attempt for kappa not equal to 0. And at that time it will be doable. So this is a crucial step here. And in this case, R naught R over R squared is minus, and that's equal to E, so this goes away, so this E sine theta, D theta. If we make that substitution, so this is 2 times our minimum, our maximum, E5, this is equal to 2 times. What is our minimum in here is, since we are making a substitution theta, so our minimum takes the value R naught over 1 plus E, and our maximum is R naught over 1 minus E. This is E sine theta, D theta, and that's E squared minus E squared cosine squared. Did I get this limits correct here? Maybe I should have. Yeah, I want to. I think I did the opposite, right? I should write this first. So our minimum here is equal to R naught over 1 plus E, and our maximum is R naught over 1 minus, right? That's the maximum and minimum. And if we substitute this here, then we know that theta here, right? If I say that R is equal to R naught over 1 plus E, so that theta comes out to be equal to 0, and this will be theta of pi. So you start from these quantities already known, and that leads you to it. And this immediately you say that, oh, that's 2 pi. That's 2 times pi. So the perihelion or precession of the perihelion is equal to 2 pi minus 2 pi. That's equal to 0. Right? That's what we know from. For a Kepler orbit, this is equal to 0. Kepler orbit is for the case when kappa is equal to 0. So this is the definition of the precession. For kappa equal to 0, that's 0. Now we repeat the same problem for kappa not equal to 0 and proceed from there. So first, a challenge, right? Okay, if that's so simple, we should see it convey. Let's see what are the challenges. Okay, so let's immediately do this for this problem, right? And do the same substitution there, and we do our minimum, our maximum. So this is let's do our minimum. What should I call this? Yeah, D5. Right. So D5, our minimum to our maximum is equal to R naught ER over R squared. Now we have E squared plus minus. kappa. Make the same substitution again. 1 minus R naught over R is equal to E cosine theta. And you get, so this is our minimum or maximum. So this is 0 to pi. This is the E sine theta, d theta. And this is E square minus E square cosine square theta plus kappa and some function R naught over R. Example could be R naught over R raised to 2 or R cube, for example, a cube of that. So that's equal. Still removed, yes. That's E square sine theta. I want to cancel that with that. So this is equal to 0 to pi E sine theta E theta. This is sine theta. So again, I pull that out here, sine theta here, and I get 1 over 1 plus kappa over E square until now we are doing everything exact, right? We haven't yet used perturbation. Now use the perturbation. This is small. You're claiming kappa is really tiny, and it is necessary that whatever else comes in here, whatever that number comes in here, that should be, this should be smaller than that. So if you were to expand that, this will be 0 to pi d theta, and this will be 1. The series, remember 1 over square root of 1 plus x is 1 minus 1 by 2x, so on. So this is minus 1 by 2, and that's minus again. So that's equal to minus 1 by 2 times kappa over E square sine square theta times f of r. Is that clear? And the first term is actually the kappa equal to 0 term, if you were to notice that. So my change, the precession of the perihelion is 2 times this minus 2 pi. The first term goes away, right? 2 times this. So it is minus of 0 to pi times kappa. I'll bring it out. So it's, since I multiply by 2, so that's kappa over E square, let's say. And I have d theta over sine square theta. And oh, I should be a little careful here. When I made the substitution, this was an R dependence, right? So I should change this. So this was R naught over R. I have to substitute 1 minus E cosine theta now. Right? All the R's has to be replaced with thetas. So I should do that. And this goes in here. So this goes in here. So 1 minus E cosine theta. Sorry about that. Preoccupied. Preoccupied with hiding few steps, which I'll reveal later. So this f of 1 minus e cosine theta. And that's a leading contribution. I'm dropping the rest. Think of an example for our f of r naught over r would be just r naught over r cube, for example. Right? This is an interaction we have here. This is 1 over r. It could even be 1 over r squared. Next leading power in an interaction. So you could say if sun was not really spherical, so that would be a 1 over r cube term that will show up. So this could be 1 over r square or r cube. R square is the best to keep the leading order. I think let's keep r square. I think your homework is r cube. So let's put r square. And then that would mean that this is just 1 minus e cosine theta square. Right, and that is square. And one would think that this is an easily doable integral. That's just trigonometric, but there is a challenge. What is the challenge you see here? Is there something that you see that is bothering? If you were to do this integral, you will realize that there is a divergence in this, because when theta is equal to 0 at both 0 and pi, this actually diverges. So if you were to try to calculate this, it's not straight forward, but that's a spurious divergence in the sense that the overall quantity is finite. It's just that when you really try to evaluate at the limits, it is having trouble there. So, or if you were careful in doing that, you can encounter this. So, and since we are interested in analyzing this for various other configuration at one stroke, it is easier if we avoid this completely. So what you do for that is so the next step. If we can do this integral, then we immediately get the precision immediately. Right? So instead, we will now go around this so that we fix or we don't encounter this divergence. How do we avoid that? It's just basically a trick again. How can we avoid that?
When did you say it's convergence? Divergence.
In this, the integrand at theta equal to 0 is at 0 is infinity, right? So there's a 1 over infinity, and again at pi there is a 1 over infinity. Right? So that makes it harder to analyze that integral at a general scenario. If you attempt, we need a quiz, right? Do this integral. Doing might be asking too much. Plot this integral. Right? Plot 1 minus e cosine theta whole square over sine square theta. As a function of theta along the angle theta. And e you can put take the situation for Earth, right? E is 0.02 for Earth.
From 0 to 5.
Yeah, 0 to 5, right? That's what interesting. 0 to 5. Like this will be the 1 over sinus cosecant, right? It will have that cosecant feature which blows up at the 0 and but integrand blowing up doesn't mean that the limits cannot be done. It's just it is more tricky to process it, like logarithmic divergence. Log is divergent, but that doesn't mean that you cannot do any integrals with log. Like it's just requires a little more. Right. So here's a trick to proceed this. So you want to avoid this divergence, right? And remember, this is a series expansion. It's only the first term that has the divergence. Right? It's you can say that this is an artifact of the perturbation. Like the divergence really is not there in the system, but the perturbation expansion gave in the divergence. So perturbation makes it easier, but then this is the price you pay for that. And so you want to avoid that. So how do you avoid that? So let's do that here now. So what I will do is, so there's a trick now, go back. So this is our denominator, right? So we're going to use a trick. So notice, let's do derivative with respect to E. E is an innocent quantity here, right? That's just the eccentricity of the system. It's just a parameter sitting there. But let's do the derivative with respect to E of the square root quantity. So it is in this sense that this is not a homework problem. To get this trick to go from, to make this observation, I'm sure someone had to have a lot of insight in that and probably land up wherever, whichever paper you got the idea from. This is now, what is the derivative of this? Let's also put F1 over E there. What is this equal to? What's the derivative equal to? There is no E here. There is no E here. Right. So that's the only quantity. That's a square root. So I'll start with the 1/2, and this comes down, right? E squared minus 1 naught R plus kappa. And then take the derivative 2 times there, but 2 times that cancels this E here. It's just this. Is that clear? And that's the trick to avoid that divergence that's coming from the perturbation. Because what you practically do is that you've taken this to the numerator, and then this issue doesn't come up anymore. Is that the thing? Okay, so proceed and do the same substitution again. Like, so now this can come out of the integral completely. So this is equal to our minimum, our max, d5 is equal to 1 over E. This can come out of the integral. Our minimum, our max, our naught, ER over R square, and now it's the numerator. Make the same substitution. This is 1 over E. Partial derivative of E. This is 0 to pi. This is E sine theta. Theta. And this is equal to this time we can say this is just E sine theta, E square sine square theta. Maybe I should take it out. No. Plus kappa times 1 minus R naught. This is 1 minus E cosine theta. Whole square. Did I get all this? Yeah, actually, pull this out. So if I pull this out, so this is E square sine square theta, and then this is E square sine square theta. I was afraid that that would be a divergence and throwing up again. But this sine square theta, when you expand, cancels that sine square theta. Okay, so that's equal to 1 over E partial derivative of E. Expand this out again. Right. E square sine square theta theta. Series expansion 1 plus 1 by 2 this time. Kappa over E square 1 minus E cosine theta whole square over sine square theta, and there are higher terms which we don't want to keep. What's the first integral equal to? Sine square theta going from 0 to pi. Sine square theta going from, help me. So sine square theta, d theta going from 0 to pi. If I go from 0 to 2 pi, probably this is having a periodic term that's a 1 by 2, right? So this is equal to pi. Because sine square theta is I think 1 minus cosine 2 theta over 2. D theta 0 to 2 pi. This is periodic, that contributes 0 there. And this is 2 pi over 2, so that's pi. The squared quantity doesn't average out to 0 all the time, right? Even though like average is 0, but it's, variance need not be 0. So this is pi. So this will be pi over 2. So this will be 1 over E, partial derivative of E. So that's E squared times pi over 2. Right. Let's get rid of this. And the next term here is plus E square cancels out, sine square cancels out, and there is a kappa over 2 times integral of 0 to pi d theta 1 minus E cosine theta, the whole square. Straightforward integral. Again, appreciate the fact that no divergence, right? The sine square, somehow we move the divergence up and got rid of. This is equal to derivative of E square is 2 times E. E cancels out, 2 cancels out, that's equal to pi. That is a kappa equal to 0 term, right? Because when you multiply by 2, that is exactly 2 pi. That should go away. And the answer now is you have to do plus kappa over 2. Or let me write this as 1 over E by the partial derivative with respect to E kappa over 2. Let's do this integral. So this is 0 to pi d theta 1 minus 2 times E times cosine theta. And the next term is plus E squared times cosine square theta. Cosine theta goes from plus 1 to minus 1 in 0 to 2 pi. So this doesn't, so this integral goes to 0. So what we have here is pi plus 1 over E partial derivative of E kappa over 2 times this integral is pi, this is 0, and plus E squared integral of cosine square theta going from 0 to pi, exactly like earlier. It will be a 1 by 2, so it is pi by 2. So how much is the perihelion shift? That is pi kappa over 2. So that is a again derivative of 2 times e that cancels out. So it is plus kappa times pi. So the total perihelion shift is equal to, so delta phi, we write it here. Yeah. One more step. Delta phi is 2 times pi minus pi, so that's kappa. It's kappa times 2 pi. Remember, kappa is really tiny, right? So it's a fraction of 2 pi comes in there. And it is just because it is 1 over r square that this integral became so simple. In your homework, what I asked you to do is that do the same thing for a cube. So most of the analysis remains the same. It's pretty much your whole class terms, except here this will be a cube. Right? This integral here is what changes. So it's only the last few steps that changes. Okay. But there is a cheat that you can do. Okay. But before I do that, any questions? Any questions? Yes.
The two pi.
Oh. The 2 pi here. What I did was that when I do the derivative with e square, 2 times e comes, right?
Mhm.
The 2 cancels here.
Okay,
the 2
the
comes
cap
here.
on the outside.
And then, so you're saying there's a kappa over 2 then, right? Oh, maybe it's 2 there. And this is probably pi. Because there are 2 factors of 2, right? One of the 2 goes away. And still I have left out with a pi by 2. Then I multiply by 2 pi because there is a definition of this has a 2 in it. Right. So when I multiply that 2, that goes away. So it is kappa times pi. Okay. That's what it is. Any other questions? There is a catch in here. In the process of saving time, I purposefully made a mistake, and the mistake was in the following place that, and this happens most of the time whenever you're doing perturbative analysis, you have to be careful what all changes. You made a perturbation, and I assumed here that our minimum and our max remain the same. Like here, our minimum was r naught over 1 plus e. This is r naught over 1 minus e. That's an e-dependent quantity, an eccentricity dependent quantity, and I assumed that it's the same. When I went from here to 0 to 5, that's a swindle line. That's not correct. This does depend on e. So what you have to do is that, but I still want to do this, right? I want to take this out, derivative out. I still want to play this game. So I have fixed those errors. So that means to say that when I write here, you have to subtract the derivative with respect to this, derivative with respect to this. Here I have taken care of only the derivative with respect to e square. I have neglected the derivative with respect to these 2 quantities. So if I want to fix that, I want to subtract those 2 quantities out. That can be done. It just was done in the lecture. That's so you have to follow that piece. There is 2 more terms in here. So there's a small cheat I made that changes the answer a little bit, but overall the idea is good. Did I clarify what I said? So this is not, when I went from this step to here, this is actually an e-dependent quantity. So I will subtract those quantities out. I will subtract first term and subtract second term, because I have not taken care of the e-dependence. Another common thing in perturbation, it's very hard to see where all the dependencies are. When you perturb your system, you want to keep your answer as similar as possible. That's a common ignorance one can make.
We get the same results when we.
No, because if you keep this term, this will change. Okay.
For the homework, should we do? these
Yes, if possible. If possible, keep it. Yeah. Homework, yeah. Do you want to keep it on? Okay, how about that? Optional. it's optional out to you guys, because this is the end of the semester. I understand that all of you guys are busy. If you just do it this way, that's good enough. And that's what Landau does, by the way. In Landau's book, he doesn't, the answer he writes, he doesn't keep the first and second term. So if Landau has done that, you guys can also. I'm sure Landau knew what he was doing. It's not that it's an error or anything. For simplicity of presentation, we neglect those. They're not negligible. So yeah, you can do that, but if you want, I'll appreciate it if you have the time. If you don't have the time, don't worry about it. But at least mention something. Yeah, don't just at least write that, yeah, we are neglected. That's something like that. Okay. 2 minutes late, but on time as per plan.